The transformative role of artificial intelligence, AI, in computer network devices. In this presentation, we'll explore how Edge AI brings control, awareness, real-time action, and scalable evolution to IT networks. We begin with AI's current role in network infrastructure, then we zoom in on Edge AI, how local intelligence is driving real-time action, saving resources, and adapting to its environment. We'll also cover deployment challenges and end with a look at future trends. AI enables intelligent traffic, fault, and security management. AI is transforming not just what networks do, but where they do it. Let's focus on three areas where it's already making a major impact: network traffic, fault, and security management. Those are the places where networks most often slow down, fail, or get attacked. First, there's traffic. Traditional networks react to congestion after it starts. AI predicts where slowdowns will occur and reroutes the traffic in real time before users notice. Google's B4 backbone used deep reinforcement learning to do just that. Next, fault management. Rather than waiting for alerts or complaints, AI spots anomalies early, like packet loss or latency spikes, and acts automatically. It's not just alerting, it's self-healing. Imagine a router quietly rebooting itself before anyone notices. And finally, security. AI learns what normal traffic looks like and flags anything out of the ordinary. If your smart fridge starts firing off DNS requests at 3 a.m., AI shuts it down fast, and there's no need to wait to apply a rule set. Now, let's talk about where this is happening, because the answer is increasingly right at the network edge. AI at the network edge enables real-time local decisions. Instead of pushing all traffic and analytics back to the cloud, we're putting intelligence on devices themselves, in routers, switches, and access points that are physically close to users and data sources. One of the key advantages of AI at the edge is its ability to act instantly. Instead of sending data to the cloud, devices can process and respond on site, which is crucial for time-sensitive applications like autonomous systems, industrial automation, or smart security. It reduces latency, boosts responsiveness, and allows decisions to happen where data originates. Companies like Qualcomm are already designing edge AI hardware to make this possible, deploying models directly in network devices to run real-time inference, not just data routing. So when we say AI at the network edge, we're not talking about science fiction. We're talking about networks that can think and act right where data lives. Now, let's take a look at how this works, especially in wireless networks where every millisecond counts. Edge intelligent GP-Bandits enable low latency, adaptive decision-making directly on wireless infrastructure. Cloud-based analytics are powerful, but too slow for fast-changing wireless conditions like interference, mobility, or rate control. Edge intelligence solves this by moving adaptive decision-making directly onto infrastructure, like base stations, edge servers, and even devices. One method gaining traction is the Gaussian Process Bandit, or GP-Bandit. These models balance exploration, trying new options, and exploitation, using what works, while managing uncertainty. Think of a Wi-Fi router that automatically learns which channels deliver the best throughput in your home. Instead of blindly cycling channels or sticking to just one, it uses a GP-Bandit to model channel performance over time and intelligently switch. Scale that up, and you have self-optimizing networks in 5G, 6G, IoT, or enterprise data centers. Originally compute intensive, these optimization algorithms now have been optimized to run efficiently at the edge. This enables real-time tuning, adjusting things like beamforming, handoff, or power levels without round trips to the cloud. The result? Wireless systems that don't just connect faster, they adapt smarter. But speed isn't the only benefit. Moving intelligence to the edge also helps reduce bandwidth, strain, and energy consumption. Let's explore how that works. Edge AI reduces bandwidth usage and energy consumption. When AI can process data locally on a router, switch, smart camera, or mobile device, it doesn't need to send every raw packet to the cloud. Instead, it filters, compresses, or summarizes the data, transmitting only what's relevant. That saves significant bandwidth, especially in high-volume settings like factories and smart cities. TDK notes that edge devices are even learning to recognize which data matters most, optimizing transmission based on context. Then there's power. Edge devices are often small, remote, and battery operated. AI enables event-driven behavior. The device wakes up, decides what to do, and goes back to sleep. No constant cloud chatter, no wasted energy. As AI Business puts it, Edge AI unlocks low-power use cases once thought impossible, like smart sensors that run for years on a single battery. And this isn't just a performance boost, it's what makes widespread deployment possible. To scale intelligent networks, devices can't be power hogs or data fire hoses. They need to be smart, selective, and efficient. And that's exactly what Edge AI delivers. Let's look at how learning and context awareness are emerging right at the edge. AI at the edge enables learning and context awareness. Until now, we focused on how AI processes data efficiently, but the real power emerges when these systems begin to learn, adapt, and act based on context. On the left, we see that evolution. At T1, the device is simply collecting raw data, motion, temperature, audio, whatever the sensors detect. By T2, it's identifying patterns, distinguishing noise from signal, and recognizing what matters. At T3, it adapts, adjusting its behavior based on what it's learned, and it's doing all of this locally with no need to consult the cloud. Covey et al. Show that even low-power devices like wearables are starting to support this kind of autonomous on-device learnings. The Siemens view on the right shows how this plays out across industries. In factories, for instance, sensors might adjust their alert threshold based on machine wear. In retail, a camera might ignore foot traffic during store hours, but flag motion at night. This is where Edge AI goes beyond efficiency. It becomes context aware, making smarter decisions because it understands the environments it's operating in. This isn't just reacting, it's learning and evolving in place. And that raises the next question. What happens when thousands of these adaptive devices work together? That's what we'll explore next. AI at the edge scales through coordination and cloud collaboration. Now that we've seen what a single edge device can do, the next question is, how do we scale? One smart device is useful, but hundreds, maybe thousands working together? That's where things get powerful. This diagram from Liu illustrates a three-tiered architecture that enables that kind of scale. At the base is the resource layer, physical world entities like sensors, robots, wearables, and even people. These devices leverage AI to collect data and often act on it in real time. Above that is the edge layer, local gateways and servers that coordinate those devices. Think of it as a brainstem, making fast decisions, routing data, and manage localized intelligence. At the top is the cloud layer, where deeper analysis, long-term learning, and system-wide optimization happen. Insights from the cloud are trained, refined, and sent back to the edge. The key is bidirectional intelligence. Devices send feedback up, and the cloud sends updates and new models back down. Cisco calls this an AI native network fabric, where intelligence isn't centralized, but shared and distributed across the infrastructure. Without coordination, you've got a bunch of isolated smart devices. With it, you have a network that learns, adapts, and scales. But building that kind of system, it's not easy. In the real world, there are a few, let's say, sharp edges to Edge AI. Let's talk about the challenges. Edge AI brings powerful benefits, but also real-world deployment challenges. Edge AI holds real promise. Faster responses, better privacy, reduced cloud dependence, and scalable intelligence. But those benefits come with challenges. Speed is a major advantage. Local processing enables low latency response, but edge devices often lack the resources to run larger models effectively. Privacy improves when sensitive data stays local, but putting intelligence on the edge means every device becomes a potential attack surface and must be secured. Edge AI can operate with less reliance on connectivity, but without the cloud, some functionality is lost, especially for complex updates or shared learning. Efficiency is a big draw, but optimizing models for constrained devices requires significant engineering effort and cost. Model updates are tricky. AI systems need retraining, and coordinating updates across thousands of endpoints introduces version control issues. And while Edge AI can scale, real-world deployment means working with diverse hardware and inconsistent infrastructure. So while the potential is real, deploying Edge AI at scale demands thoughtful design and long-term investment. Now let's look ahead. Where is this technology heading, and how will it shape the networks of tomorrow? Edge AI is advancing rapidly, driven by smarter models, better chips, and hybrid cloud integration. Edge AI is advancing fast, and several trends are shaping where it's headed. First, TinyML, or tiny machine learning, like the GP-Bandits discussed earlier, enables machine learning on ultra-low power devices. These compact, efficient models make smart sensing possible, even on wearables or on Internet of Things or IoT endpoints. Second, edge cloud hybrid systems are becoming the norm. Quick decisions happen at the edge, while the cloud manages complex processing and updates. Third, there's custom AI chips, like Edge TPUs and the Jetson Nano and Qualcomm processors. They're boosting performance while keeping energy use low. Fourth is federated learning, addressing privacy and communication costs. Devices train models locally, sharing only results, not raw data. And finally, network-aware optimization lets models adapt in real time to changing bandwidth or latency conditions, improving performance in unpredictable environments. Taken together, these trends show that Edge AI is more than a technical convenience. It's becoming a core design strategy for modern intelligent networks. As we wrap up, let's take a step back and summarize what we've covered, where AI fits into networking today and what it means for the future. In summary, AI is reshaping computer networks by bringing intelligence closer to where the data is created and decisions are made. Artificial intelligence is no longer confined to the cloud or the data center. It's becoming embedded throughout the network, from routers and switches to the edge devices, just a hop away from where data is generated. We've seen how AI enhances control, responsiveness, and adaptability. At the edge, it enables smarter, faster, and more resource-efficient systems. As networks evolve, Edge AI will be central to making them more intelligent and scalable. As we've seen with techniques like GP-Bandits, intelligence once limited to centralized systems can now operate directly on wireless infrastructure, bringing real-time adaptation to places that were previously too constrained. The key takeaway is Edge AI is not just changing where decisions happen, it's redefining how networks think, act, and scale. These are the resources used for this presentation. Thanks for viewing the video. We'll see you on the next one.